URETEK Holdings. This is the Injectable Barrier webinar. I'm going to go ahead and get started here with a few administrative notes. During the presentation, all microphones will be muted. So if you have questions, use the questions area on the right side of your screen. You can put your questions there. They'll get to me, and then I will answer them at the appropriate time. At the end of the presentation, we're going to have a Q&A session. Now, we've got about probably 20 slides in this presentation, and I'm going to do a brief overview of a case study as well. So that's 30 more slides, which I'm going to have to push through pretty fast because we've only got about an hour's time. So at the end of that, we'll go ahead and have that QA session. So feel free to jump in, use the chat option on that toolbar on the right, and you can get your questions out there, and I will get to them as quickly as possible through the presentation or at the end. And we're going to have an hour of professional development hour credits available. Now, you'll have to look to your specific state to make sure that they are acceptable in each state. So all states are different, and I know that we've got a nationwide audience. So please make sure that they are valid for your credential. So let's go ahead and get started here. Who is URETEK Holdings? Well, we are an innovator and leader in subsurface geotechnical polymer application, traditionally with non-environmental applications, which is specifically the subject of this presentation. But what we've done is we've applied our knowledge in other areas to the environmental world. So, and we'll get into some of the details in a little bit. So we've got about 25 years of experience, and as you can see, quite a few successfully completed projects. We've got whatever insurance and bonding might be necessary for even the largest of jobs, $5 million aggregate for bonding, $2 million per project. And as far as insurance goes, we carry comprehensive general liability, all the statutory requirements with respect to workers' comp and automobile and what have you, but also railroad protective liability insurance, pollution liability insurance, and that's a big name for the environmental folks, and longshoremen's in case we're working around water. So we do have those capabilities. We've got a very well experienced management team that for years served with Westinghouse Westinghouse Environmental Unit. That's all on board here at URETEK Holdings. We've got an exemplary safety culture. Our EMR of 0.75 is about probably the best there is out there in the industry. Now, we do serve the infrastructure, the commercial, residential and government entities. We're headquartered in Lakeland, Florida, but we've got a nationwide footprint. So we reach out through 31 states, and we've got 30 sales engineers out there to service any needs that you might have in your specific geographic location. So while I'm on this slide, I'll also just mention a little bit about myself. I am a 35-year environmental career professional, having served most of my time with chemical waste management and the Westinghouse Environmental Unit. And I specialize in remedial construction and on-site treatment technologies. Now, I guess at the start of my career, I worked on the Love Canal, which was one of the first Superfund sites that there was out there, and more recently worked on the Deepwater Horizon spill incident in the Gulf of Mexico. So a very interesting career path. I'm a licensed general contractor in multiple states, and I'm a current board member and past chair of Florida's Construction Licensing Board. So let's get into the presentation itself. Injectable barrier. We put those two terms together, separately defined as the act of or process of forcing a liquid into something, and a barrier obviously is something that prevents movement. So an injectable barrier is injection of a substance into the earth, and what we're using is a geotechnical polymer, which is a twin component material that basically is injected through a tube, which you'll see here later. And the picture actually to the right shows some of the tubing being put into the ground. But what we do is we mix this polymer. There is a reaction that takes place, and the material is surgically injected into a strategic location or locations, and it rapidly expands from 15 to 22 times its initial liquid volume, and travels through the soil and performs basically the function of permeating through the soil and turning that soil into a monolith at the specific injection location. So when you put a few of them together, you form the barrier. So the applications for the injectable barrier, there's two main ones, and environmental containment and control would be one. And the first example of that would be construction support. And that would be to support an operation to install a feature of some sort, whether it be a foundation, underground pipes, in the example of working on a right-of-way and installing storm drains or sewer pipes or what have you. So that would be the first environmental control feature that we can support. And the second one is for environmental remediation, and that would be to actually to contain a plume of contamination within a certain area to prevent its migration out of that specific area. The second application for the injectable barrier is for seepage management, and it would be used around dams, dikes, levees, water control structures, and so forth. And most of what we're going to talk about today, which is the environmental control feature, because of the audience that we have here today. So the purpose of an injectable barrier, there's really two of them. One is a temporary in nature, and the other one's permanent in nature. Temporary would be for construction support, and basically that would be to support an operation that was passing through an area, and that would be a perfect example to if you were installing a pipe through a DOT right-of-way, for example, in which you had a contaminant source off-site and you didn't want to draw it on your site during dewatering operations to install the pipe. So that's truly temporary in nature. And basically when you're doing your design, you take into account whether it's temporary or permanent, and based on that, the amount of material, the injection frequency in terms of depth, the depth interval, and the amount and the spacing is going to vary. Obviously for a temporary feature, it's going to be less material, less rows. For a permanent one, like for water cutoff and for permanent environmental containment, you're going to want to have more material in the ground. You're going to want a more impermeable barrier in place. So, and the end result is, or the deciding factor is the cost-benefit analysis of one or the other. So the injectable barrier, how it works is it's injected at varying depths, and it's specific to the it's specific to every application. For example, there's no set dollar value or amount of material injected per linear foot of barrier wall. All different, every site is different. There's different soil features, there's different hydrogeologic features, there's different purposes. So we don't have a per foot figure. So we inject at various depths. Subsequent injections next to or above or below bond to each other to form a barrier. And the barrier may or may not provide absolute coverage. Obviously for a permanent barrier, you want that absolute coverage, so you're going to inject more material. You may have a tighter spacing pattern. For one that is temporary in nature, you don't have to have absolute coverage. You're just looking to restrict water flow through it because it's of a relatively short duration time. So what this illustration shows, or animation shows, is tubes being inserted, 3 elevations here for this one. And basically what they do is all of the spheres of material that are injected form a monolith that forms a tight grid and actually cuts off movement of water from one area to the other. And this shows basically what we've got when we do a line of injections. So one of the things I want to do, I mentioned this earlier, is I just want to run very quickly through a case summary that was presented at the Florida Remediation Conference in October of 2013. It was performed by a separate company, so this is not a URETEK work product. It was basically done by a contractor that has a contamination assessment and remediation services contract with the Department of Transportation. All of the work that was done was third-party certified, and this white paper was actually repeated at the National Association of Environmental Professionals annual conference in St. Petersburg Florida in April of 2014. So I'm going to jump over. I'm going to pull up the case study. And this was done by Handex Consulting and Remediation, and many of you may know that name. Going to get it to full screen here. So it was co-authored by Tim Harmon and with HCR and with Vince Fusconi, who is with the Department of Transportation. And I apologize right now because I've got to go through this fairly quickly, but it will be made available to anybody that would like to see a copy of it. It's got some very good information in it, but it is 30 pages, so we don't have a lot of time, and I do want to leave plenty of time for questions. So this was a highway improvement project in Palm Beach County. This is an overview of the actual site, which was a street corner that had a gas station. And everyone knows that the gas stations on every street corner at one point in time had some sort of a leak, whether it was from the tank, the pumps, the dispensers, or a catastrophic failure. All gas stations pretty much have or had leaks at one point in time. So the proposed the work involved installing a deep structure, and as you can see, the gas station was on the southwest corner of that intersection. And the contamination shows here in this next slide. So the reddish contour shows the contaminated area. The dotted circle, red circle, shows the predicted dewatering radius of influence, which was about 75 feet. So the cone of depression obviously would move towards the proposed structure, and had nothing been done here, contamination would have been drawn into the dewatering system to install this structure, thereby requiring a on-site treatment system, a granular activated carbon treatment system, which is fairly expensive to install, big footprint. It's going to slow your project down. You've got to have NIPD's permits and all the associated costs. So that was a major factor in selecting the URETEK injectable barrier as a solution. So the team was the Department of Transportation, the car contractor, URETEK, and Bergman Associates, who's a local CEI that supports a lot of Department of Transportation work. So the concept was to install a rigid structural geotechnical polymer, which had been previously used by the team for another purpose, which is the first project that we did just north of this site for DOT. It had been done on another site in Fort Lauderdale, and so it is a relatively new concept. And the first application was in Palm Beach County, and it was proposed by the DOT that we do the work and utilize an existing technology in a new application. And there were actually a couple of awards that were given to department employees, and I'll get into those a little bit later. So the product description, what we use is the URETEK 486 star material. It is a twin component, high density expanding resin system, and basically it's always been used for the last 25 years or so for undersealing slabs, void filling, lifting of settled pavement, slabs, foundations, what have you, stabilizing weak soils under structures, holding excavations open, and basically it is it's a material that's manufactured by Bayer Material Science under a patent owned by URETEK. That is, it's a proprietary material. It's not available to anyone outside of us, and we keep a tight control on that because it is a patented product that we are very familiar with its use. The nice thing is it's hydro-insensitive, so we can inject this material above the water table. We can inject it into the Veda zone and deep into the groundwater, and it's not impacted by the presence of water. So the chemical reaction still takes place and is not impacted. It is a closed cell material, so when it expands, it forms a CO2 gas. So the resins are held together on that CO2 gas. They form a closed cell. They travel through the soil, and they cure very rapidly. From the time that we hit the trigger on the gun to do the injection to the time that we hit the induction phase, which is when it starts to react, is only 4 or 5 seconds. And within 15 minutes, the material is fully expanded and it's cured to about 90% of its maximum density. Full density is achieved within about 1 day. So we do have the National Science Foundation, the NSF 61 certification, and what that means is the material has been tested for its leachable characteristics, and it does not present any risk to human health or the environment. So this shows a couple pictures of the material. Expanded foam here at the top where my mouse is, and that is basically material that outcropped from an injection. So looking at that, you can see that it's a foam material, basically a polyurethane foam material, very similar to the great stuff you get at the Home Depot, although a very different formulation here. So this shot here shows the material shot into a sandy soil mixture, and you can see what it's done here is it's turned it into a monolith, and this is just a small outcrop that was cut out, dug up, cut out, and photographed for the purposes of this presentation. This is an injection tube, and this is actually how we do the injections, is through these tubes, which are sacrificial, and they're driven down to the depth in which we do the injection. And I've got a question that came in here, and let me go ahead and see if I can answer this. Question came in: how would URETEK apply to sealing ballast rock under a railroad line that penetrates a levee? Okay, so the ballast rock actually presents a little bit of a difficulty in driving our tubing. So what we would do with that is we would use a driller to get us down through. There are occasions when we can drill through with a rotary drill on a Hilti vibratory machine that can get us down through it. Sometimes we can. Sometimes that rock will stay in place when we've drilled, and we've done that on many occasions and been able to successfully inject below the ballast to lock things in place. There are times, though, that we have had to drill down through it using a drilling rig. So in that circumstance, it would be a little bit different process, but we still can get it done. So getting back to the white paper here, and the next page, this is the plan for the site. The contamination, again, in the red. The cutoff wall, our injected wall, shows in the orange, and that is this wall right here that's in an L shape. The proposed dewatering well points are shown by the green dots, with the structure being shown in green. And what we show here are temporary monitor wells 1 and wells 2, which one was inside of the contaminated area, on the inside of the injectable barrier wall, the second one being on the outside. Now, there were other wells that were installed and other piezometers that were installed for monitoring depth to groundwater and gradient, but they're not shown on this for purposes of simplicity. So the plan continued to install a cutoff wall, design and install a cutoff wall. From a mechanical standpoint, there was a dewatering fluid treatment system that was actually installed on the site just in case we had a problem, because the contamination was so close to the area of extraction. We wanted to make sure that we did have the option to be able to treat materials if the circumstance arose, and I'm happy to say it did not. We saw no movement whatsoever of that plume. And then the management of the plan. A lot of people came together, a lot of stakeholders in this project. There was a huge monitoring and sampling plan put in place, some very detailed protocol, and a lot of observation in making sure that everything came together. Obviously, when you design a program like this and you've got so many variables, you want to make sure everything stays constant throughout so that your operational parameters match your design parameters, so you don't have any mistakes. And one of those could be something as simple as a contractor telling you he's going to install his dewatering well points at 15 feet, so his base elevation for extraction is 15 feet, and then he drives them deeper, not knowing the impact it's going to have to our barrier wall. So governing assumptions on this project, the predicted dewatering flow rate at steady state was 75 GPM. It was modeled in ways in which it's typically done. So they looked at the soil lithology, depth to groundwater, the dewatering depth, and in this circumstance it was 15 feet. the aquifer thickness and the hydraulic conductivity, which this site was fairly fast. So, and the groundwater flow here was to the north-northeast, which, if you recall the this plan here, flow to the northeast means that that plume was moving towards naturally moving towards our barrier wall. So the barrier wall was basically between the contamination and dewatering area, about 125 feet. The injection interval, we set the barrier wall from 8 feet to 20 feet below surface. So what we did is we put injections at 8 feet below surface, 11, 14, 17, and 20 feet to form an interlocking grid, and then we repeated that every 3 feet horizontally across land surface to form a tight interlocking grid. And we did use the URETEK 486 star material for this project. The installation time, it was very quick. It was about a 4-day installation time. Obviously, the material, I already mentioned the NSF certification and the properties, excellent chemical resistance to the products that we were protecting against, so no issue with respect to that. So this basically just shows a dewatering fluids treatment system. This is typical to what's installed on a site like this. Probably doesn't require a lot of discussion on this call, but it'll be included in the package that's sent out to anybody that requests it. And I just had a question that came in. What density was used in the barrier case study? What we used was a URETEK 486 star, 4-pound regular. So the density of that material is 4 pounds per cubic foot. So the collaboration on this was monumental on this project, just because of all the stakeholders. So we had the Department of Transportation, we had the environmental contractor, we had URETEK, the CEI firm, the roadway contractor, their dewatering subcontractor. Obviously, you've got to have all the environmental regulatory agencies involved. So Palm Beach County was on, the South Florida Water Management District. URS Corporation was involved, and everybody recalls is going to know that name. They were involved because the gas station that we were protecting against had an active treatment system on site, so they wanted to make sure that we didn't impact their ongoing treatment. And then we had Palm Beach County Utilities was involved also, because they had some major utilities coming through the project area. And this shows basically is a plan view of the utilities, and the you know, as luck would have it, there's always something in place that impacts what you want to do, and that is a high pressure gas main, a 4.5-inch diameter gas main that went right basically, and if you see my cursor here, our wall followed this path and then went down this path here. So we actually had the gas utility out there with us, assisting us to make sure that we didn't impact their line in any way, shape, or form. And most everything else out there, we didn't have too many impacts with, but they were, most of it was overhead, but we did have some underground, but we were able to get around it pretty easily. The nice thing with the URETEK 486 star is that it's injected through the small tubing, and if we've got utilities we need to work around, this is a soft installation method. It's not like sheet piling, which would have been, it couldn't be used here because of the utilities. But the sheet piling is very invasive. The tubing we use to install, if we've got utilities we need to work around, typically we'll use a hydro lance. So we'll drill through pavement, use a hydro lance, and that way we can do a soft push through it and then put our rods through that and be past the utility without any impact whatsoever. Again, this shows the injection points laid on the plan. 41 points, 3 feet on center. And again, the depth intervals I mentioned earlier, we installed approximately 12 pounds to 20 pounds per elevation point. And as you are shallower, you inject less material. As you get deeper, you inject more, because as you're deeper, the soil is theoretically denser. So it takes more material to travel the same distance, and we want to get that 3-foot radiance, that 3-foot sphere installed from top to bottom. We did install 40 pounds for the corner point, and that would be at this point. So what that meant is we installed 50 to 100 pounds per point as we travel horizontally across land surface. So we injected a total of 4,299 pounds, and the total length of this barrier is 125 feet. So just some pictures here, and I do have a couple questions that have come in, so let me take a look here. I've got a question. Have most state, federal environmental regulatory agencies accepted this method as an equivalent to a bentonite slurry cutoff system, or would permeability testing still be required? That's a good question. For the most part, we want to make sure if we're doing something that is temporary in nature, we can take a look at the soil lithology, the hydrogeologic characteristics, do some modeling, and figure out how much material to inject. If we're talking about containing a contaminant on a site for a long duration, let's just say semi-permanent, we're going to want to do some permeability testing. And that would be probably a precursor to getting any environmental regulatory agencies buy-off that the process, the solution is acceptable to them. We're actually in the process of doing some of that right now, and I'll get into that just a little bit later. But great question, topic of a lot of discussion from our end right now. So the installation, what these pictures show is the top left shows basically the method that we use. You can see the tubing there in the center of the screen laid on the sidewalk at varying depths to inject to the target elevation. We typically will use a scissors lift or a man lift to do the injections, and we use a vibratory hammer to drive the tubing into the ground. And what we do is we use a cone tip on the bottom of these tubes, and what that does is helps guide it through the soil to get the injection depth. And then when we attach the gun to it and start injecting, that tip is blown off just by the pressure of the reaction. So this picture here shows completed installation of tubing, and what you can see here is each one has got, and this is 3-foot interval spacing horizontally, but each one's got 5 tubes in the ground, and that matches up with the 8-foot, 11-foot, 14 feet, 17 feet, and 20-foot elevation installations. And this line here is the part that goes along the east-west road, and then we turned the corner here and went down the north-south road. Again, another picture here just showing the crew doing the injection work, and you can see the hose. The hose goes from the unit, which is a single truck unit, to that contains all the equipment. And I don't know for sure if we've got a picture of it here. We do not. But anyhow, what we take is a single unit out to do the entire job. It's self-contained. It's got the product storage in it. It's got a compressor, a generator, the reactor unit, which proportions the material. It heats it up. It brings it to the correct temperature, the correct pressure, and the correct 1-to-1 ratio of the ISO material to the polymer material. It's delivered through the hose that you see here. It's a twin terrain delivery hose, so there are 2 hoses that go through this to go to the gun that this gentleman is holding. And this hose is all heat traced, so the temperature remains constant from the time it leaves the unit to the time it's injected. And the material doesn't come in contact with each other until the point at which the trigger is pulled and the material flows down the tube to the injection site. So next page here shows the monitoring plan, which we had a groundwater monitoring plan to do hydraulic monitoring. 4 times a day we were measuring the temporary monitor wells just to make sure that there was no, especially in monitoring well 1, which was inside the barrier. Monitoring well 2, we definitely wanted to see some movement because we were dewatering. And from a contaminant standpoint, each well was monitored twice a day for benzene, toluene, ethyl benzene, and xylene components, or volatile organic aromatics, as well as PAHs, which are polynuclear aromatic hydrocarbons. So the operations on the site were conducted in some nice pictures here. This is the dewatering unit that's set up, a well point system. You can see right about this area is where the installation was taking place. Work took place for about 7 days, and the system was comprised of a dewatering pump, a baffle box, a transfer pump, an air diffuser, and a closed storm sewer discharge system. So the flow, this is interesting, calculated was about 75, and what we ended up with was 78 gallons per minute maximum, 75 on average at startup, and when we came to steady state, about 40 gallons per minute. The environmental contractor used a in situ level troll to monitor all the monitor wells, which is an automatic device, and they were inserted into the 2 temporary monitor wells and run continuously through the project. What this does is shows the results of movement of groundwater. Temporary well 1 being this one here on the inside of the contamination. What we can see here is there was a rain event right when we started the work, so you saw a little jump there in the groundwater level, and then as we started pumping, you saw a depression start there, but almost instantaneously came right back up and pretty much achieved just barely a tiny little bit of drawdown on the contaminant side of the wall. And then what's shown here is another groundwater, another precipitation event. So that's reflected in this spike. So the second one is temporary monitor well 2, which was on the outside of the wall where the excavation was going to take place. And you can see this nice decline in the groundwater level down to -3. It jumped up a little bit, and that was part of the rain event influencing it. And then again, some more rain right here. And then it started to level off as we achieved steady state. So some nice results, nice graphics there. So again, the contaminants were monitored twice a day, and also the dewatering system unit was monitored twice a day, both the influent and the effluent, just to make sure that nothing was escaping the service station area. So the results, as you can see here, the temporary monitor well 2, which was on the clean side of the injection wall, everything was below the minimum detection limits of the laboratory, or the quantifiable limits of the laboratory. So nothing whatsoever showed up there. On the influent side of the liquid that was extracted by the dewatering system, same results, and the same thing for the effluent. So we saw no breakthrough whatsoever.
Bob,
we did have an unintended consequence. DOT had a, yeah, go ahead.
Certainly. I've got a few questions here if it's a good time to address them.
Absolutely.
Okay, great. If at a later date we had to excavate the barrier wall area, does that require any special handling or disposal?
What you wouldn't want to use a shovel. So you wouldn't want to try to hand shovel it out. It's going to be a pretty dense material. You definitely need to have a machine to do the work, but very easily a hydraulic excavator would do it, or a combination backhoe such as a John Deere 310 or a Case 580K would easily cut through this material. I would think that I would associate it with a flowable fill material, like a flowable grout fill material.
The question also asks about special handling for disposal. I think the regarding the materials disposal requirements, environmental requirements.
Okay, there are. Thanks, Robert. There are no special environmental disposal considerations that come into play. The material, when it's cured, is chemically inert, so there are no characteristics that would require any special handling from a personal protection standpoint or health and hygiene standpoint, nor are there any impacts with respect to its disposal. And any questions that might come from that could be easily satisfied by the fact that we've got the NSF 61 certification on the product, which means it's safe to use around a potable water supply system.
Okay, next question is, how do you identify below surface obstacles?
Typically what we do is before we start a project, there's a couple of steps that we take. The first one being call the state underground utility locate center, and that's basically all the states are in compliance with the Federal Underground Utility Protection Act. So it's a free call. All the utilities are located by the various facilities, whether it be the electric, the gas, the communication, water and sewer, whatever, they're all located by the utility companies themselves, or the facilities themselves. Now, we take it a step further. Typically, we also bring a GPR unit to the site. So we do a geophysical scan of the site to try to make sure that we identify all utilities, and a lot of times it's to fine-tune what the electric and other utilities have already told us, but what it does is gives us more quantifiable definition of not only the physical placement from a horizontal standpoint, but also the depth. So it allows us to work around, and that's one of the nice benefits of this solution is we can work around utilities very easily. You can't install like the cut and dry, past use probably for something like this would be to try to install a sheet pile wall, which is a hard physical iron wall that you drive in the ground, but you can't do that around utilities. Nice thing is we can inject around utilities and not impact them. So great question. Anything else, Robert?
Yes, a few more. Does the expansive pressure create difficulties with existing utilities? Is the pressure extreme enough to begin fracturing surrounding soils?
Well, it can be, and that's a good question also. It can be. If we were to just to hold the trigger down and pump and pump and pump material, absolutely. There's a couple of consequences, though. One would be it's very costly if you just want to hold the trigger down. And the second thing being that you're really not accomplishing a whole lot because we would be fracturing the soil, and we don't necessarily want to do that. We want to permeate it more than fracture it. Now, there's a point where we get deep, where we got dense materials that we might start to fracture a little bit, but typically the gun operator has a sense of the feel of the flow of material through that gun and can tell what's going on. The gun won't pulse as much for him, so he knows what's going on down there. As far as impacting a utility, the only utility that we're going to come close to having an issue with would be vitrified clay pipe, which is in the ground has been there 70 years or so, and it's in very poor condition. It's not been used for many, many years in the public right-of-way anyways. But historically, those have been lines that have been the subject of many leaks and collapses and what have you. So the nice thing about our product is that it seeks the path of least resistance. So it goes really where it needs to go by itself, kind of like water, seeking the path of least resistance. One of the drawbacks is that working around something like a vitrified clay pipe, we're going to find that break. We're going to find that joint that's leaking, and we're going to put material in it. Which I'm going to go ahead and onto this slide here. I'll answer more questions in a second if there are out there, Robert. But the unintended consequences of this slide I've got right now is exactly that. We did get into a pipe. The material here shown in this picture is material that got into a very large storm drain, and the reason was there was a failed joint that the DOT did not tell us about. They knew about it. They were going to repair it. Now, the nice thing is that we actually, when we injected the material to form our barrier, it actually followed the path of resistance. It found this leak in the pipe, so it permeated the soil. It densified it, so it provided a structural support to the road surface above. It got into the pipe, and by doing so, it sealed up that leak. And DOT actually was quite happy because they got that fixed, and all they had to do was cut this foam material out of the pipe, which took them a couple of hours of time. So they were very happy of that unintended consequence. And with that, Robert, were there any other questions at this time?
A few more. We also had basically addressing the application of injectable barrier in limestone soil media, such as in the case in the Miami-Dade County, to prevent seepage.
Okay, actually we have done a couple of projects on State Road 7 in Hollywood that have had limestone formations that we've been able to drive through. And typically what we'll do is we will drill using a rotary drill to get down through any material to get our injection points in place. But we did a very large project actually, if I recall, it was about a 600 and somewhere around 650 linear foot barrier wall on a site in Hollywood that had arsenic contamination. And we worked on that project for AECOM and installed a barrier around the contamination to allow them to come in and do cleanup work within those confines. So, and that was done in a limestone medium. And although it slowed us down, it didn't stop us. It's just we just have to find a way to work through it, and we did so on that site and finished it actually right dead smack on the project schedule. So that was a good, successful project for us. And I actually have a one-pager that I'll come to at the end of this presentation that shows that site.
Okay, this was regarding the case study. What caused the initial drawdown at TW1?
It was probably a result of some water going, what we're theorizing, it was likely the consequence of some material going underneath the barrier. So there was an upwelling on the dewatering side that caused the initial drop on the TMW1 side. And as soon as everything else on the clean side reached a bit of equilibrium, that stabilized and the water level went right back up to where it was. Now the nice consequence is, and we don't show it on this case summary, is all of the monitor wells on the contaminated site that were a function of the remediation system that was put in place were monitored before and after the injection work, and nothing changed. So we really didn't impact that area whatsoever.
Okay, how does material go along subsurface corbelled stone block foundation?
Any foundation, what it's going to do is, and I'm not sure if I understand the question completely, but what it would do is basically it would travel horizontally beneath the foundation, and obviously seeking the path of least resistance. So if there was a concrete foundation, for example, it's going to move mostly horizontally, below or beside the foundation. And if I didn't answer that correctly, please, whoever asked it, ask again, and Robert will forward that question back to me.
Bob, we have a few more, but I think let's go ahead and hold off on questions and continue with the presentation for the moment, and we'll hold off on the questions for a little bit later.
Okay, that sounds good. I will go ahead then and jump onto the next slide. This really just shows the remediation timeline, and it was a fairly quick time frame to get this all put in place. Even though it shows a little more than a year, well, about a year and a half or so timeline, there's a lot of events that took place there. But basically, the stuff right in the middle, this is basically the meat of the project right through here. So very quick time frame to get things done. This is a very accelerated process that we can get in and out very quickly. This shows there was a remediation system in place. I mentioned earlier on the contaminated site. This shows it was actually a soil gas vapor extraction and treatment system. This shows some of the results of it. And one of the unintended consequences of this barrier wall is we did impact the remediation system, but we did impact it positively. What we did by putting the wall in place is we created a way that the system drafted and pulled more of a vacuum and actually treated this contaminated site in a much quicker, accelerated schedule than was originally anticipated. So that was a nice unintended consequence. And as you can see from this slide here, the total petroleum hydrocarbon concentrations came down very, very quickly after we did this installation. So they reached, as you can see, asymptotic levels at that looks like May 6th of 2013. So this site was cleaned up much quicker than what they had expected. So the conclusions that HCR came to on this, and the Department of Transportation, is that the injectable barrier is very effective as a groundwater cutoff wall. It's very cost effective, easy to install. It can form a permanent barrier. It's green in that it's a very low footprint. You don't have a lot of the equipment there that you would have to install, let's just say sheet piling, for example, or to install a groundwater recovery and treatment system. And then in general, this last part is talking about the remediation system that was in place, and what it showed is high sparge pressure readings and greater vacuum readings near the barrier. So very effective tool there in controlling flow, not only of groundwater for its intended purpose, but soil gas vapor for its unintended consequence. And that's it for this. I'm going to jump back into the presentation here. Robert, any questions while I'm transitioning here?
Certainly. For soil stabilization, i.e. keeping sand from migrating on the backside of a sheet pile retaining wall, would you just reduce the pounds per injection or pounds injected?
Repeat that question, please, just so I can understand it correctly.
Sure. The question is regarding soil stabilization, and an example was keeping sand from migrating on the backside of a sheet pile retaining wall. Would we just reduce the pounds injected?
Well, we could do it. Thanks, Robert. Yes, we could do it that way. We could either reduce the pounds that we injected. We could inject at multiple elevations with closer spacing using that cut back poundage per point schedule, and we can also pulse the gun. So what the operator does is he's injecting material. Rather than holding the trigger down, he can hold it down for a bit and let off and pulse it. So these shooting injections, and he's got to be careful with that, because if he doesn't keep that moving fast enough, it's going to set up on him. Like I said, the set time is very quick. Induction phase is about 4 or 5 seconds after we pull the trigger. That's when the chemical reaction takes place and we start to get expansion. And then, within basically a couple of minutes, it really starts to set up. So the viscosity goes from its initial, which is somewhere around 200 centipoise. It goes from 200 centipoise within probably a minute's time to being something that is fairly durable and is not going to move anywhere. So there's a number of ways to hold a sandy soil at the bottom or at the base or at the backside of a sheet piled wall. And that can be done either for a construction effort for land work, but also for a sheet piled wall is installed to contain a waterway, like a seawall.
All right.
Any other questions, Robert?
Yes. Is the foam degradable by petroleum products?
Generally, no, it's not. It has excellent chemical resistance to petroleum products. Actually, very good chemical resistance to anything you get from an automotive service station, volatiles, semi-volatiles, in older stations, methyl tert butyl ether, and tetraethyl lead. There are a couple of materials we have problems working around, and that would be acetone. But quite honestly, the concentrations necessary to affect the material that would have to be present in the soil or the groundwater, I don't think you're going to see those in concentrations that are going to affect the barrier material. The other thing that it can impact over time is highly concentrated acids like hydrochloric acid, sulfuric acid, nitric acid, and hydrofluorosilicic acid. But aside from that, there are not many chemical materials that impact the 486 star product.
I've got a few more. Do you want to address them now, or do you want to wait a moment?
Let me go ahead. Let me run through the slides. and then we'll address them at the end. That way, I get through the slides, we'll get through the hour here in case anybody does need to drop off, just so they can catch the whole presentation, and then we'll sum up with questions at the end. So to put together a project, what we would need, and I guess this is a tool for everyone that's on the call. What we need to have are construction plans. When you're looking at a project, we need to have construction plans and specifications. So we're going to want to see a plan view, the profile, the specifications. We're going to need to collect all the contamination data, and there's a various means for collecting all that information. We want to know, this is very important, we want to know the geotechnical data. So we're going to want the soil boring logs, which shows the lithology, the groundwater elevations. All that equates to the groundwater flow direction when combined with other borings. We're going to want to see transmissivity data. We're going to want to know the construction methodology. What's taken place? What's taken place that that you would need our services in the first place? Are you installing pipe? Are you installing a structure? What else is going on? So we need the type, the depth, the duration of construction. The same thing for a dewatering event. It's very important to know how much material is going to be taken out, what the duration is, the depth of the dewatering, because that all equates into our design. We're also going to want to know, and this is very important, any potential utility conflicts and potentials for delay. The utilities, although we can work around them, they do slow us down. So we're going to want to know what's underground before we get out there and get started. So everyone knows time is money, and when you get out for example, on a site like this, you've got a lot of people out there, and everyone has payroll and has equipment, and you don't want to slow them down. So it's best having all the information you can right up front, so you have a plan to move forward. So for design considerations, we're going to look at doing a horizontal and vertical grid pattern for the injection methodology. Typically, it's 3 foot by 3 foot spacing between each of our injection points, and that 3 feet by 3 feet is both horizontally and vertically. Our shallowest injection is going to intersect the groundwater elevation, with the deepest injection being at least 2 intervals below the dewatering points. So I already mentioned we're going to increase quantities as the depth increases. And to put that in perspective, let's just say we're injecting at the 8 foot level. We're probably going to want to install 15 pounds or so. When we go down to the next interval, which is 11 feet down, we want to bump that up by 5, and so on and so forth till we get to the bottom elevation. And that's because material is just generally denser. Your soil is denser, so it's going to take more material to travel the same distance as you go deeper. So on a lot of the work that is done when it's temporary in nature to support a constructive effort, a single row of injection points is typically the design credential, but depending on the duration and the end effect, multiple rows should always be considered, and those multiple rows will be offset from that 3 by 3 pattern. So they form an intercept of the precision of the first row, and that's basically so you've got a protection factor put in place. And the formulation we typically use, I should mention that URETEK has about 9 different formulations of the 486 star, but the one that we typically use for the injectable barrier is what we call the 4-pound regular, and that's the one that has the greatest propensity to be able to travel a distance before it starts to react, but also it just loves working around water, so water doesn't impact its reaction, its placement, or its cure, or its long-term durability. So this is kind of a rendering of the what it would look like to inject material in the ground. And as you can see here, we don't necessarily form a continuous absolute barrier for a temporary injectable barrier. What we're relying on is that we're creating a monolith where the material is injected. It's following the path of least resistance, but we inject enough material that it consolidates the soil and it compacts it between injection points to the point that it reduces the transmissive properties. So water is not allowed to flow freely from one side to the other. So when we get on the site to do the installation work, we've already mentioned doing the utility locates. So we want to meet the locator or facility owner if possible. It's always good to have that utility location service there with you, so you can tell them exactly what you're doing, exactly what you're placing, and they can tell you exactly where their facility is located. There are times when we do have a utility that goes through the barrier and we can't install exactly in that 3x3 pattern. And what we'll do there is we'll use a setback from, let's just say, a sewer pipe that goes through the barrier. So we can't, let's just say we can't install directly above or directly below it. What we'll do is we'll use offset points on either side, and we may just increase the quantity of material so that we get coverage to travel that distance to cover the gap that for the point that we can't install. So another consideration on the site is maintenance of traffic. Sometimes we will handle it ourselves. Sometimes it's handled by other people. So the reason I put this in here is because maintenance of traffic is very, very important, and that you ensure all your workforce adequate protection. Also want to make sure we've got PPE and safety equipment for everything we're doing, and we're always working in a point where we're facing traffic. So we want to be in a position where workers can see exactly what might be coming at them. So typically the placement of the injection tubing is in clusters. We'll put 3 to 5 rods per hole, and the 3 to 5 would reflect to the 5 would be the 5 injection elevations of the example for the case study, which was 8 foot, 11 foot, 14, 17, and 20 feet. So 5 rods would go down that one hole. And the tubing is about 5/8 inch in diameter. So you can get those 3 to 5 in, let's just say, a 2-inch diameter hole cored down through pavement. So we're going to hydro lance to weed around shallow utilities, and that's so that we don't impact those utilities, but we still get our point placed strategically. And sometimes we also hydro lance to jumpstart our deeper injection. What that does is allows us to accurately place, because the first few feet of driving that tubing is critical in making sure that we get to the target area. So if we hydro lance to jumpstart those, we get a much better tolerance for meeting the exact placement location than as if we had not. We do collect drilling debris immediately. Anything that comes to the surface, like on a road surface, we get it off the road because that can always be a hazard. I always consider protection of the storm drain system. If you do get a heavy rain that comes down, it's going to carry some of that material. The drill cuttings is going to carry it to the storm drain, and you don't want that. And we always use aerial lift devices while driving the rods. And that is because when we use the a man lift or scissor lift, we can get a planometer on our tubing to ensure that we've got that exact 90-degree placement so that we get a perfect placement of the rods down to the target depth. So from a monitoring standpoint, this is very important. When we're doing injection, historically, the polymers have been used for by URETEK for stabilizing soils, for undersealing concrete, for realigning pavement, and for realigning foundations. So it's got tremendous properties to be able to move things around. So as we're doing the injection for the injectable barrier, we want to make sure that we're monitoring the pavement and any ancillary structures. So we're going to have a laser out there with target readers on directly over the area that we're injecting. We're going to have one in the periphery. We're going to have one on the curb and gutter, one on the sidewalk, or any other structure that's there that might be impacted. And then going back to the comment I made earlier, that the material follows the path of least resistance, it can move around pretty freely. And for example, if you've got a tree root that's rotted, over time, the material will find that void, and it'll travel and it'll come up somewhere else. So we do monitor very carefully. We always consider, if we're working around storm drains, we always consider, in storm sewers, we consider using either a downhole camera to monitor it, or using a robotic camera to remotely look inside to make sure that we're not filling it up because there's a hole into the pipe. And then the other monitoring that takes place typically is a CAR contractor, which is a contamination assessment remediation contractor. So that's your environmental folks. They're out there monitoring for the environmental parameters. So they're taking samples out of the monitor wells. They're monitoring the inflow and the outflow to make sure that we don't have any excursions. So we've done quite a few projects to date. Every single one successful. The first one is the subject of an award that the DOT received, the design team as well as the implementation team received. The two I mentioned earlier in the limestone were the State Road 7, the arsenic site, and then the State Road 7 PAH site. So 7 projects so far. We've dealt with BTEX contamination, which is benzene, toluene, ethylbenzene, and xylenes. The arsenic contamination, the PAHs, which are polynuclear aromatic hydrocarbons, and then the DNAPLs, which are on the last project we did, which are dense non-aqueous phase liquids, which would be dry cleaning solvents. So we did, last project we did was a dry cleaning solvent site. And that was the site of a deep installation for a conflict structure that was right dead smack in the middle of a major state highway intersection. Very interesting project. So this is the first project. This is the project profile and the first project we did. Some nice graphics there. This is a picture of the unit. This is the only thing that shows up on the job site. Everything's self-contained in that unit. A shot here of our operator doing the actual injection work, and a shot here, and you can see the actual tubing coming out of the ground, where we've got some rebar protector on it just to make sure no one gets cut by the exposed tubing. So this project was interesting. At a cost to the DOT of $99,500 for the work that we did, under their estimation, we saved them $900,000. So very interesting project. Next one is the State Road 7 barrier. This was the arsenic project, and we're running out of time, so I'm actually going to jump through this fairly quickly so I can get to a couple questions. But this was a nice project. We did the work in 10 days. It allowed the environmental contractor to come and clean up the arsenic contamination in a very quick and time-efficient and economical manner. We'll get everybody a copy of this presentation so you can see some of the publicity we've had. Would like to mention that we're doing a presentation at Florida's Association of Environmental Professionals National Conference, a statewide conference in September. Like to see anybody that's attending that see our presentation. And we do have an upcoming webinar on commercial and industrial foundation lifting, and that's set for September 11th. So you'll probably see an invite for that, and would love to have everybody in attendance there. So please make sure to connect to us here by the various social media you see. And Robert, if you want to go ahead and throw some questions out there, please do so.
All right, great. So let me go right into it. So what type of soils has this material been tested in? How does it work in silty clay soils?
It's been used mostly in limestone soils and sandy material. It has been used in organic, high organic content soils. It's not been used much around clay. Now we can work around clay, but clay actually forms a natural barrier to the transmissive. It actually impacts the transmissive properties of soil. So generally, we wouldn't be called to work much around it unless it was a layer, a specific layer of material. And we would obviously inject above and or below a clay layer, depending on whether it's a confining layer or not. So we would actually work around it and not necessarily within it, because within it we would fracture it, and we probably don't want to do that.
We have our President Corey Carlson on. He wanted to address the railroad question from earlier. Hi, Corey, are you on?
Yes, I am. First of all, thank you everybody for attending. Greatly appreciate your interest in the last few webinars we've had, and thanks for listening. The very first question today was about how does our material perform in rail ballast. And just to add to what Bob Moody shared, currently we have a study underway with the University of Wisconsin for how our chemical grout performs with rail ballast, and we could provide the article to any of those who are interested after this webinar. But Professor Tinjum at the University of Wisconsin had a thesis or thought that chemical grout used in existing rail ballast would perform better than brand new ballast. And so far in the lab test, that has proved to be true. And so not very often do you have a rehabilitation method that actually works better than a remove and replace option. So this fall we will be doing a live test at a rail in Illinois to verify that what we're finding out in the lab is actually working in the field. So we have an article from University of Wisconsin in regard to this testing. If anyone would like that, please let us know. But I just want to follow up with that rail ballast question. But thanks everybody for attending.
All right, thank you, Corey. Bob, I have a question about how is the resistance to ground temperature changes of New England climates?
The only thing that now I guess the question could be, as far as the reaction takes place, as far as the chemical reaction in placing the barrier, the reaction is exothermic, so there's heat generated during the process. And basically the exotherm is 190 degrees above ambient temperature. So placement's not going to be impacted by climatic changes anywhere pretty much in the continental U.S. So we won't have any impact to being able to install. Obviously, in the deadpan of winter, it's going to be difficult because we're going to have to drill down below the frost line to do the work. But the reaction is still going to take place just fine. There's no issues with once the material comes together, with the reaction taking place, material expanding, none of the properties are impacted. And then if the question was, is there an impact in the change in temperature from season to season in the New England area? No, that wouldn't impact the material whatsoever. Once it's set in place and cured, there's no temperature change that would impact placement or final use of the material.
So once it's in the ground, it's fine. The temperature effects will not affect it. It's more about the installation.
That's correct.
What if you want to inject horizontally, like 30 feet to seal under an existing slab?
We've actually done that, and typically, the length, the depth that we can inject at is limited because of the fast nature of the reaction. And it's a simple function of the time it takes from the point that the material is mixed at the impingement exit of the gun and travels down the tube till it starts to cure. And once it starts to cure, obviously it's not going to travel through the soil. So there's a limitation from that standpoint. And that's variable because it's impacted by temperature, pressure, and a couple of other factors. I can say that we have done a 60-plus foot shot horizontally to get inside a sanitary sewer that had failed in the middle of a major highway, leading to partial roadway collapse. What we did was had a slip-line pipe put in place, and we were able to install bulkheads at either side and then inject the product. The span was 120 feet, and so we were able to inject from either side for a 60-foot horizontal travel to be able to place the material to not only fill the void, but to lock that slip-line pipe in place and also provide restorative support to the highway surface that started to collapse. So we've gotten 60 feet horizontally with this product.
Sorry, I was on
Questions,
mute.
Robert?
Yep, no, I was on mute. I apologize. Have you ever encountered a subsurface void, and what would be done if this would happen?
Yeah, we actually encounter them quite often. Sometimes they're anticipated, sometimes not. And basically, a subsurface void is, if we pump the material into it, it'll expand, it'll fill the space up, and in a very rapid time, it will cure and take care of the void space. And we work in a lot of karst formations in which you do have voids or sinkholes, and so the material is actually a very effective solution to filling those voids up. The only impact, if you didn't anticipate it, I think the question was, if you encounter an unanticipated void, is it would take material to fill it. So there's going to be the resultant cost in material that it takes to fill that void space.
Okay. Did the wall help the remediation efforts on the contaminated site by preventing the contamination from migrating outside the wall?
No, the contamination, the contamination that was, the remediation system that was on the site was a soil gas vapor extraction and treatment system. So they basically put a draft on the soil through a pipe network system, used an induced draft fan to draw a vacuum off the soil and run it through a vapor phase granular activated carbon canisters to strip it of its volatile components. So basically what was taking place is the vacuum being put in the ground was vented in all directions. It pulled its source or its makeup air from all directions from the underground. When the injectable barrier was put in place, what it did is it stopped flow from one end, and it allowed the system operators to draw from the extraction points closest to the wall. And what it did is it basically concentrated the flow of air across the contaminated media and allowed it to be sucked up much quicker than anticipated and actually clean the site up so that they could pull the system and walk away from the site.
All right. What is the injection sequence? Do you start with the shallow pipes first or deepest? Do you complete all pipes at a point first, or do you complete all the first depth pipes along the line and then go to the next depth, etc.?
Well, there's a couple of ways of approaching it, but generally speaking, and again, this is all pretty much something that when we look at all the data that comes in on the site, we'll determine an injection plan. But basically the thought process is that we inject from the top down. And the reason for that is that the material has a little bit more of a propensity to move upward than it does move horizontally. But also you've got the fact that you've driven a number of rods through the soil, so you've disturbed that soil. So you have a vertical pipeline that if you were to do the bottom injection first, it could potentially travel up that space, and it could impact our ability to inject at a shallower installation. So what we're going to do is we're going to inject from the top down, and we're going to work on one point first. Then we're going to hopscotch over, so we're going to skip the next point, and let's just say our spacing is 3 feet horizontally. We're going to move to the 6-foot point, and we're going to do the injection at that one, and then we're going to come back and do the intermediate one, again from the top down. And that's generally our injection sequence for the barrier wall installation.
Okay. How do the physical properties of the injected material change over time?
Well, from the point of injection, obviously you're in a liquid state during the injection. Very quickly thereafter, within 15 minutes, you're at 90% density. Within 1 day, you're at 100%. So it solidifies, densifies, cures very, very quickly. But the effect over time is that the material probably has a couple of 100 years of life to it. There have been many studies done, one by DuPont, in which they tested the physical properties, the long-term properties of polyurethane resins, and they found that at least 60 to 70 years is probably what you could use for design considerations as far as the longevity of material in soil.
Can you control the cure time with the mixture ratio?
You can control it with the ratio. You can also control it with the temperature. Generally speaking, our set temperature on the reactor unit is 92 degrees. We can cut that back to slow the reaction, and what that does is it allows for a deeper injection because of the time it takes to travel, but also slowing it down some can sometimes increase the amount of travel you get underground as well. So yes, we can. Now we typically don't. We typically use just a straight 1-to-1 ratio because that's the chemical makeup of the material is based on that perfect 1-to-1 proportioning for the reaction to take place correctly.
Okay. Are there? Oh, I'm sorry. How will it, this is a clarification on the northeast question, but it says how will it stand up to the freeze-thaw cycles in New England?
It's not impacted whatsoever. We actually have affiliates that work, and I guess I should have mentioned that URETEK is basically a global has a global footprint, being on 6 continents. Obviously, nothing going on in Antarctica, but we do have an affiliate network that operates in Alaska, and so obviously no issues whatsoever with the work done there. Obviously, the only consideration for injection work is that you've got to work with the season. But no, there's no impact with the freeze-thaw cycles whatsoever.
Okay. Consider a 48-inch unreinforced concrete sewerage line, gravity 100 years old, that is about to strengthen by CIPP lining. At invert, there is a deflect allowing groundwater into the line, which stops the CIPP from being installed. Would this product be able to surround the sewer line to temporarily keep the groundwater out, say 10 feet ahead, sometimes more?
Absolutely, yes. That is actually one of the solutions that we provide routinely to departments of transportation throughout the United States. So yes, what the material does is there's a number of ways to inject. Obviously, this is probably something that we want to inject from the top down. And in that circumstance, what we would do is drive tubing so that we would be at an angle to try to get underneath the pipe at the 6 o'clock position, inject there, but also we'd probably want to put a couple of points so that they intersected just above the flow line, and let's just say at the 4 o'clock and 8 o'clock positions, and inject more material there. And what that does is it's going to densify that soil that it comes into contact with. It's going to obviously stabilize it, but it's also going to encompass the pipe and in effect most likely seal it off. And we do routinely seal pipes similar to this on a routine basis. Now the second way to do the installation, I should add, the one is top down where you're using the tubing. The second, if it's large enough, and let's just say 30-inch or greater, we can inject from the inside. Obviously, some considerations there with confined space entry, having our certified people on the job to do that work and having the necessary equipment. But we can get inside a 30-inch or larger pipe and run through that and actually drill through the pipe and then use fittings that tap into the hole you've drilled, attach the gun to that, and we can shoot directly behind and into the soils. So we're actually attacking it from the inside out in that circumstance.
All right. If using a method-like injection technique on a vertical concrete wall at 2 foot on center, would the path of least resistance allow a water barrier to form and close to the wall surface?
Read that one more time, please, Robert.
Sure.
I'll make sure I fully understand it.
If using a method-like injection technique on a vertical concrete wall at 2 foot on center, would the path of least resistance allow a water barrier to form close to the wall surface?
We would likely displace that water. Typically what we do, and there's some very excellent, if anybody has the opportunity, jump online, hit YouTube, lot of information there. But generally speaking, any water that might form against something like that, when we do the injection work, we're going to displace that water. So we're going to push it out of the way. And we frequently see that when we're doing an injection work, even with the injectable barriers where we're injecting down deep. We see air bubbles and we see water spurting out of the ground at highway joints, at the joint between the curb and the gutter, and so forth. So we would likely displace that material.
Do we have any references in the Northeast region?
Any references, meaning?
I would imagine project references.
I'm sure we do. Most of the work that we've done for injectable barriers has been in the Southeast. It's a relatively new, it's application of an existing technology in a new manner to serve a different purpose. So, like I said, most of the work we've done has been in the Southeast.
I think for applications outside of the injectable barrier, this is Corey Carlson again. Our product is on New Jersey as well as New York DOT specifications. We actually just did a project this week for a high school in New Jersey, and a couple weeks ago for a stormwater authority to stabilize and seal cracks in manholes. So we do quite a bit of work in the Northeast, and we'd be more than happy to provide some of that information after this webinar. So please reach out, and we can provide you some references for the Northeast.
Okay, that looks like it for questions, except for one regarding the PDH certificates, and I'll go ahead and answer that if that's okay, Bob.
Sure.
Okay, so after this webinar, we will be sending out an email that will go to an online form on our website. Just fill out the form and state that you'd like a PDH certificate, and we will then respond with your PDH certificate. Please give us a couple days. This was a very well attended webinar, and so to personalize each one of those PDH certificates will take a minute amount of time. The only other thing I'll note to that is also through that form link, there will be a downloadable version of the presentation you saw today, as well as a link to view the video again of the presentation. And that's it for me, Bob.
Okay, thank you, Robert. And I'll add that there's the one other, what we'll have available is not only this presentation, but we'll have the case summary. We'll have the video, which the video is a great one that was prepared for the injectable barrier application. And if there's any other information requests out there, please send them on in. We'll be happy to answer any one of them. We do have project profiles on all the projects we completed, so those are available as well. And I guess in closing, I'd like to say thank you very much. Appreciate the great attendance today, the great questions that were asked. And if we can be of any service whatsoever, please do not hesitate to reach out by either phone or email or whatever means are out there. So again, thank you very much. Look forward to seeing all of you on the next webinar coming up that we mentioned earlier, and hope everyone has a great day and a great weekend. Thank you.